Hello, my dear students. In the past lecture, we discussed the method of integration by substitution. So in this lecture, we are going to discuss another method of integration called integration by parts. The method of integration by parts works when the integrand function is a product of two functions such as this integral, integration x squared ln x, integration exponential minus 3x cosine 4x, etc. Or maybe a single function such as tan inverse x, ln x, and sine inverse x. So in each of these integration formulas, we noted that the substitution method cannot solve these kinds of problem, maybe except this integral problem. So the integration by parts is a suitable choice for such a kind of integration. Now to see the idea behind the integration by parts, we shall remember the differentiation rule for a product of two differentiable functions f and g, where the derivative of the product of f and g is the derivative of f multiplied by g plus f multiplied by the derivative of g. So if we have an integration problem of this form, f times the derivative of g with respect to x, then this integration is, this antiderivative, the derivative of this function is just the product of the function f and g, and we subtract from that the integration of the derivative of f multiplied by g of x dx. So the core idea behind the integration by parts is to simplify this integral by first noticing that the integrand function is expressed as a multiplication of two functions. The first function is differentiable. We can compute its derivative. The second function is integrable, so we can compute it is integral, such that this integral here can be computed easily, okay, or at least easier than the original problem here. So this form here, explained by equation 2, is called the formula for integration by parts. And there is another more popular form for this integration, obtained by replacing the function f of x by u and g of x by v. So this equation becomes integration u dv equal uv minus integration v du. And this function, this form, is called formula for integration by parts. Now to see how the method of integration by parts works, we consider this example in which we wish to evaluate integral ln x dx. So in this problem, we choose u equal ln x because we know the derivative of the ln function. So dv becomes dx, and we know the integral of dx. Therefore, when u is ln x, du is the derivative of ln x, which is 1 over x, and then we multiply by dx. dv is the x, so the v is the integral of the x, which is x. And here we shall notice that we ignore the integration constant when we integrate dv to obtain v. Now we apply the formula of integration by parts. So this integral ln x dx, which is integral u dv equal uv. This is the function v, this is the function u, okay, minus integral v du. This is v and this is du. So this integral here simplifies to integral dx, which gives x. Hence, integration ln x dx becomes x ln x minus x plus constant of integration. Now we consider the second example in which we evaluate integration t times secant square t with respect to t for t from 0 to pi over 4. Here we again see that we can apply the method of integration by parts, because if we take u equal t, then we know that du is just dt. And if we choose dv equals secant square t dt, then integrating secant square t dt gives tan t, which is v. So u is t, v is tan t, du is dt, and dv is secant square t dt. So having these four quantities, we can apply the formula of integration by parts. So integration u dv, which is t secant square t dt, is uv, u is t, v is tangent of t, minus integration v du. V is tan t, du is dt, and we put the limits of integration. Okay. So now the integral of tangent t is just minus ln cosine t. So this minus with minus becomes plus. So we obtain t tan t plus ln cosine t for this integral here. Okay. And then we evaluate the integral using the second part of the fundamental theorem of calculus. So when we substitute pi over 4 instead of t, we obtain pi over 4 tan pi over 4 plus ln cosine pi over 4, as we see here. Okay, and then we subtract from that 0 times tan 0 plus ln cosine 0, as we see here. Now we evaluate. Tan pi over 4 is 1. So this term contributes by pi over 4, which is this term here. Cosine pi over 4 is 1 over square root of 2. So this term contributes with ln 1 over square root of 2, as we see here. 0 tan 0 is 0, so this term does not contribute to the sum. And cosine 0 is 1, and ln 1 is 0, so this term also contributes with 0. That means it does not contribute to the sum. So the final answer for this definite integral is pi over 4 plus ln 1 over square root of 2. We consider a third example. So we evaluate the integral of x times the square root of 1 minus x dx for x from 0 to 1. Yeah, our choice here for u is x. For dv is the square root of 1 minus x dx. Then we see that du is just dx because the derivative of x is 1 with respect to x. And v is obtained by integrating the square root of 1 minus x with respect to x, giving minus 2/3 times 1 minus x power 3/2. So since we have the four quantities u, v, du, and dv, we can apply the formula of integration by parts. So this integral equal to uv, u is x, and v is this amount. So we obtain this term here, minus integration v du. So this is v here, and this is du, which is dx. And then when we do the integration, we obtain this term here. Okay, now we substitute x by 1. So when we substitute 1 instead of x here, we obtain 1 minus 1, which is 0. So this term cancels. Here again, when we substitute x by 1, we get 1 minus 1, which is 0. And this term cancels also. Now we substitute 0. So when we substitute x by 0 here, we obtain 0 multiplied by the rest of the. So this term again cancels. And when we substitute 0 here, we obtain 1 minus 0 power 5/2, which is 1, multiplied by 4/15. And we remember that the sign of this term is negative, so negative with negative becomes positive. So we remain for us only 4/15, which is the answer for, the value of this definite integral. Let us look at this fourth example, where we shall evaluate the definite integral of tan inverse y dy. And in this example, we choose u equal tan inverse y because we know the derivative of tan inverse y, which is 1 over 1 plus y squared dy. So this becomes du. And dv is dy. So that means v is the integration of dy, which is y. So now we apply the formula of integration by part. So the integral of tan inverse y dy is uv, this is v and this is u, okay, minus integral v du, v is y and du is 1 over 1 plus y squared dy. So we obtain this integral. So this integral is easy to evaluate because we see that the numerator could be the derivative of the denominator if it is multiplied by 2. So if we multiply by 2 and we multiply by half, then this integral is half ln the denominator, 1 plus y squared. So this integral becomes is given by this formula. Now we substitute the limits of the integral. So when we substitute y equal 1, we obtain 1 times tan inverse 1, which is tan inverse 1, giving pi over 4. And in this term, when we substitute y equal 1, we obtain half ln 1 plus 1, which is ln 2. Then we will have ln 2 over 2, which is this term here. And when we substitute y equal 0, then we obtain 0 times tan inverse 0, which is 0. So this term is 0. And then when we also substitute y equals 0 in this term, we obtain ln 1 over 2, and ln 1 is 0. So this term is 0. And then the final answer we obtain is pi over 4 minus ln 2 over 2. Let us look at this problem. In this problem, we are required to find the area of the region bounded by the curve y equal x exponential minus x, and the x-axis from x equals 0 to x equals 4. So we know that the area between two curves is just the integral of the difference between the two functions. Here, the equation of the x-axis is y equals 0. So that means we say integral of x e power minus x minus 0 from x equals 0 to x equals 4, because those are the limits of the integral. So to evaluate this integral, we use the method of integration by parts. We choose u equal x and dv equal exponential minus x dx. Then the derivative of u, du is just dx, and v is obtained by integrating exponential minus x dx, giving minus exponential minus x. So now when we apply the formula of integration by parts, we see that this integral equal to uv, u is x, v is negative exponential minus x, minus integration v du, v is minus exponential minus x, and dv is du, sorry, is dx. So this integral is just, see, this negative goes out, it becomes positive, and the integral of exponential minus x is minus exponential minus x. So when we write it in a simple form, it is given by this function. Now when we evaluate, when we substitute x equal 4, we obtain 1 plus 4, that is 5, exponential minus 4, which is this term here. And when we substitute 0, then here we have 1 plus 0, that is 1, multiplied by exponential minus 0, that is 1 also. So we obtain here negative 1, and we have minus because 0 is at the lower limit of integration. So minus minus 1 is positive 1, giving this term here. So then the area between this curve and the x-axis is 1 minus 5 e power minus 4. In some kinds of integration problems, we might apply the method of integration by parts more than one time to obtain an answer for the integral. So this is an example which shows us that we shall use the integration by parts twice to find the value of this integration. So to obtain the value of integration exponential t cosine t dt, at the beginning we might choose u equal exponential t, and dv is cosine t dt. Then du is the derivative of the exponential function e power t, which is e power t dt, and v is the integral of cosine t dt, which is sine t. Now when we apply the formula of integration by parts, we obtain that integral of exponential t cosine t dt is uv, this is u and this is v, minus integral v du. Okay, so this is v sine t and du is exponential t dt. Unfortunately, the integral formula we obtain here at the right hand side had the same level of difficulty as the original problem. So we cannot evaluate this integral directly unless we use the method of integration by part again. So we try to use the method of integration by parts again to evaluate this integration. So again we use u equal exponential t and v equal sine t dt. So from u we find that du is e power t dt, and from the formula of dv sine t dt, when we integrate, we obtain v equal minus cosine t. Now we apply the formula of integration by parts. So this integral equal to uv, u is e power t, v is minus cosine t, minus integral v du, v is minus cosine t, and du is e power t dt. Okay, so when we see that this negative when it's taken out, then we have minus minus, it becomes plus. So then this integral becomes minus exponential t cosine t plus exponential t cosine t dt. Let us now take this value, okay, and substitute it instead of the integral of exponential t sine t dt here. So what we obtain is that the integral of exponential t cosine t dt is, now we write this part here as is, but instead of this part here, we write this formula which we obtain. But when we distribute the negative, negative becomes positive, and positive becomes negative. Okay, so we see that on the right hand side we have exponential cosine t dt, which is the integral that we wish to compute its value. So now we add exponential t cosine t dt to the two sides. So when we add this term to the left hand side, we obtain twice the integral exponential t cosine t dt. And at the right hand side, we remain with the rest of the terms. Okay, this term, and the constant. So to obtain this value of this integral, we divide the two sides by 2, giving this integral equal exponential t sine t plus cosine t over 2, and then we add the constant of integration. Here you have an exercise to check. It is for yourself to check that you have understood the method we explained in the previous slide. So in this exercise, you are required to find general forms for those two integral or integration problems. Okay, e power ax cosine bx dx and e power ax sine bx dx, where a and b are real constants. And then in problem 2, you are required to apply the general forms here, the integral forms you obtained from in the first question to these problems. Okay. Now we look at this example 7, where we are going to evaluate integration x squared exponential minus x dx. So again, in this integration problem, we must apply the technique of integration by parts twice to find the value of this integration. So at the beginning, we begin by choosing u equal x squared and dv equal exponential minus x dx. Then we find that du is 2x dx by differentiating the x squared, and v is obtained by integrating exponential minus x dx, giving minus exponential minus x. So when we apply the formula of integration by parts, this integral equal to uv, this is u, and v is negative exponential minus x, this is uv, minus integration v du, this is v, and 2x dx is du. Okay, this is v du. So, and then we add the constant of integration. That means, so we obtain this formula for this integration. But we see that again we have this integration formula, which came from the integration of v du. We obtain integration x exponential minus x dx. So now we need to use the integration by parts again to evaluate this integration. Okay, so we choose u equal x and dv equal exponential minus x dx. Okay, so du is dx and v is the integration of exponential minus x, which is minus exponential minus x. So when we plug these values of u, v, du, and dv in the formula of integration by parts, we obtain this is uv, and this is integration v du, which gives minus x exponential minus x minus exponential minus x. So instead of integral x exponential minus x here, we replace it by its value of integration that we obtain here, and then the integral of x squared exponential minus x is just minus x squared minus 2x minus 2 multiplied by e power minus x plus constant of integration plus constant. The method by which we evaluated this integration in the previous slide was a little bit long. So instead of saying that we are applying the method of integration by parts twice, here we introduce a short way for evaluating this integration. Since x squared is a polynomial of second degree, we know that if we compute its derivatives, the derivative of x squared is 2x, the derivative of 2x is 2, and the derivative of 2 is 0. So we end at 0. If we continue differentiating, we will remain obtaining zeros. Okay, so we stop at the first 0 that we reach. And also we noted that the function e power minus x can be integrated consequently. So if we integrate exponential minus x, we obtain minus exponential minus x. We see this function. And if we integrate this function again, we obtain exponential minus x. And if we integrate exponential minus x, we obtain minus exponential minus x. and the sequence can continue to infinite number of times. But since here we are stopping at the fourth element, I mean the third derivative, here we again stop at the third integral. Now if we write x squared and its derivative, okay, in one column like this, and exponential minus x and its integral in a corresponding column like this, now we can construct a product of these functions 2 by 2, like x squared is multiplied by negative exponential minus x and is given a positive sign, as we see here in this term. Then the function 2x is multiplied by exponential minus x, but we give it a negative sign, so we subtract 2x times e power minus x. Then we multiply 2 by minus exponential minus x, and we give it a positive sign, because here the signs are altering, starting by positive, negative, and so on. Okay, so then the third term, and when we sum them together, we obtain this one. Therefore, this integral is given by negative x squared plus 2x plus 2 multiplied by exponential minus x plus constant, and this is a same answer that we obtained in the previous slide. So this method looks, shorter than the previous method. We explain it the same method again through evaluating the integral of x cubed cosine 2x with respect to x. And we see that since x cubed is a polynomial, that means its fourth derivative is 0. Okay? So that means if we start by x cubed, we find its derivative, which is 3x squared. And then the second derivative is 6x, the third derivative is 6, and the fourth derivative is 0. On the other hand, if we start integrating cosine 2x, its first integral is sine 2x divided by 2. The second integral is negative cosine 2x divided by 4. The third integral is negative sine 2x divided by 8. And the fourth integral is cosine 2x divided by 16. So now we construct those products here. We multiply x cubed by sine 2x and we give it a positive sign. Then we subtract from that, this is the subtraction, the product of 3x squared multiplied by negative cosine 2x, okay, which we see here. Then we add to that the product of 6x multiplied by negative sine 2x divided by 8, which is this term here. And then we subtract 6 multiplied by cosine 2x over 16, which is this term here. And hence the integral of x cubed cosine 2x after simplification is given by this function. As an exercise for you to evaluate whether you have understood the previous technique, I would ask you to find the values of these integrals. Okay, those three integrals. Try to find their integration formulas using the same technique that any technique actually. You can use the first, the direct, applying the repeated method of applying integration by part formulas, or by the method which we learned in the previous two slides. Thank you very much, and I hope to see you in the next lecture.